Good afternoon, ladies and gentlemen, Mr. Chairman. It's my great pleasure to be here very much to the ECF conference, and I thank the organizers very much for giving me the chance to talk about our achievements in the last years about micromechanical modeling of fracture in metallic materials. Before I begin, let me thank and introduce my co-workers, my research assistants, Gerald Piller, who was the inspirator for many of these research, Young and Young, Sibel, and Stefan Roth, who developed resist element models. My outline is, after some introduction, I want to give a short review about local approaches to model fracture processes, continuum damage mechanics, and the direct discrete modeling of the fracture process zone. And then I go to applications of our institute. We dealt a lot with nodular cast iron in the last years, and we can simulate ductile crack resistance curves and also the ductile brittle transistor regime. And similar for ferritic steels, we focus on the effect of carbides, the competition between brittle and ductile behavior. So when we look on the length scales for fracture analysis, everybody knows similar figures. Then we have the engineering macro scale of structural components. Then we make a stress analysis and compute the loading parameters for fracture and K factors, strain interval, and so on. Materials testing people determine the critical values of these parameters, and by comparing applied load and fracture resistance, we make our positions about crack behavior. This is the daily business of most of us. No. The underlying concept of all this is that there exist near-tip fields as crack. For instance, the K field zone or the HRR in plasticity, E and Q stresses, which control the stress and strain behavior of the very crack tip where the fracture process happens in the material. And this autonomy of the fracture process zone allows us to transfer results from the specimen to the structure and vice versa. In all these continuing approaches, the process zone is only a black box. It is complex in such toughness values in one figure. And if you want to go deeper and understand what happens, we have to go to the microstructure and explore the physical mechanism of fracture which happens there. So this is required in for several reasons, not only for basic research. We know there are limitations in the classical fracture mechanics concepts. For instance, ductile fractures cannot be modeled with these parameters. So we have to simulate something in the structure. Or if you go to very brittle behavior, we have stochastic multi-crack behavior, Barry-Mann model, for instance. And in all cases, when the fracture process zone reaches a size comparable to the structure, then we have to go isolate the fracture process zone in this sense. And our aim is now to predict the fracture toughness. The fracture toughness, not the loading parameter, but the resistance of material by means of numerical methods. And this can help to optimize the microstructure of materials and to design the materials for better fracture resistance. Of course, the topic micromechanical modeling is so large, I cannot cover it today. Therefore, I give only an overview of some very recent and excellent review articles here by French group, American group, over ductile fracture and down to local approach for cleavage. I think you all know this famous research. Now I want to mainly focus on the ductile fracture mechanisms. We know it consists of formation of voids, growth of voids, and finally coalescence of voids to grow the crack in a ductile method. There exists whole zoo of ductile damage models, well-known Gerson model, Rosselet model, and many extensions by these authors for non-spherical particles, for inclusion, for anisotropic material behavior, and so on and so on. I will, as an example, go a little into detail the well-known and well-established Gerson model in its extension by Twerger and Needleman. It's, I think, not new to most of you. So it is a plasticity model for porous metals. The yield condition is described by the stress tensor, and our isotopic damage variable is the void volume fraction F star. And here is the stress space of the equivalent stress and the hydrostatic stress. We see this yield surface. These are the definitions known for the equivalent stress and the hydrostatic stress. And the triaxiality of the stress state is here the most important driving term for crack growth. It is crack growth, and what we need is a true stress strain behavior of the matrix. It is only of the matrix. It comes in here into play. So the voids grow from an initial volume F0 until they coalesce Fc, and after that an accelerated growing happens until final failure. The void evolution consists of two terms. One is pure growing of the voids due to the incompressibility of the ductile matrix ground, and the other term is nucleation. It is we can put many equations. It is a Gaussian distribution, and Fn is the density of nucleating sites. So in total, this model has hardening parameters and 9 damage parameters, which are usually difficult to determine. And all the physics is behind of these parameters. But the good story is, this is first time complete coupling between the stress and strain state of the material and the damage evolution of voids. But in total, it is a macroscopic, homogenized material model, which is well suited to implement it in the final element code, which is done already. Sometimes it's called the micromechanical model, but I would tell it or name it the micromechanical motivated model, because it has not really the capability to resolve discrete voids of the microstructure. For this model, only the density is deciding whether it is one big void or 1,000 small voids. It can be differentiated between them. But it's very successful in simulating ductile crack growth. Here, one of our old results: 3-point bending, elastic plastic behavior. And here you see the FEM simulation of crack growth by means of ductile damage. These red elements are the completely damaged elements, and this is crack growth. For this model, which has a softening and no length scale, the damage shown is confined to one element row only. And the finally makes the elements definable to damage row. So the result depends on the mesh size, which must be for a real material row. So we must be very careful if we transfer the simulations from the specimen to the structure. We have to take the same element length. So it is a result. The crack resistance curve, J integral over delta A. The blue curve is an experiment, and these were our numerical simulations. You can fit it quite well by adjusting your element size, EE. In our case, it was 100 micrometer, and some people say it is an intrinsic micromechanical atomic length scale space of voids or something like this. But I think it is a little bit unfortunate mixture between numerics and physics. But it is a pragmatic approach anyway, which is frequently used. One can overcome it by non-linear, non-local damage models. We have done it with the implicit gradient model, but I cannot go into detail here. But so the mechanics people have solved it, but on the expense of very high numerical effort. So let's come to the true discrete models of a fracture process zone. It is only a sketch. It happens not in a real material, but all effects which could happen. We have grains, we have different phases, we have particles in the grain boundary, which break, we have debonding of the grain boundary, we have formation of voids, debonding of the particles, and all these things in its discrete geometrical and material representation can be modeled. And their interaction to investigate fracture process. This is, you might see, the right way to simulate and to predict the fracture toughness. Understand the material and improve it. The disadvantage is it requires a large computational effort. Many millions of degrees of freedom we will see. And what is even more difficult, how to get all the parameters for the microstructure, geometrical material properties, interface strengths. So I go a little bit through the history. The first who tried to simulate these ductile track roads was the group around McMeekin at the end of the 1970s. So by large scale, large strain plastic analysis, they found the stress and strain state in front of a blunted notch and assumed here in this distance x0 a void, one void, and 2D with the radius r0. So we know opening stresses go like this. They have a peak about at this distance to delta, and the strains go up to infinity, and the triaxiality has a maximum, which drives this void flow. And from dimensional considerations, we can argue that the fracture toughness or the initiation toughness must be proportional to the yield strength. Sigma y is the initial yield strength. It represents the plastic material behavior and some distance, characteristic length of the material. For instance, this distance here. And there's a coefficient which depends now on the hardening, on the elastic plastic material properties of the porosity, initial porosity, the triaxiality, and all microstructural features. Similar parallels we can draw for the effective opening. Sorry, the Microsoft made some new symbol here. And the outcome of McMeekin is this coefficient C, it's a normalized fracture toughness, versus the distance x0, or we can recalculate it in porosity values. So here is high porosity, big voids, and here is low porosity, gives this dependency. It's clear for large porosity, the toughness is smaller, so for small porosity. He tried to contrast this result with data from the literature from many methods, but you see at that time the database was not as good and it was large, scattered. Later on, Werner and Hutchinson handed an idea and put the row of voids, cylindrical voids, in front of the track and found that for small porosity there is a mechanism that only one void per void grows and the ligaments are leaky. Whereas for high porosity, a whole set of voids simultaneously is growing, and we call it multiple void mechanism. This results are in the blue line. So they reduce toughness considerably. This was all 2D results. In 3D, it was done by these authors, I referred to Kim and all. They applied in front of a 3D correct one on the ligament a number of spherical voids and analyzed it. And this is again our C over the porosity. And maybe the most important result is that for 3D we have a much higher toughness than for 2D. And this is clear because in 2D we have cylindrical voids, and now in 3D the ligaments between these spheres connect as well and absorb energy. So let me come to our applications to modular cast iron. This is a very interesting and more frequently used material in engineering, especially for big casted components like the hubs or gears of wind turbines. In Germany, especially for the nuclear transportation and storage cars, castors are all made under 20 tons of ductile cast iron, or also very ductile, tempered ductile iron is attempted for railway wheels. So this has advantages. This can be well casted, net shape forming, and cost-effective production, and the mechanical properties are not as bad compared to steel. The problems are casting effects, which have regarded as initial cracks, and we have a large influence of microstructure and also the manufacturing and technology, casting, the Go-Killer, sand, and all these things, and across the thickness of the big parts, the microstructure will vary. So our aim was now to find a relationship between the microstructure and the fracture mechanical properties. And the other thing, we liked this material is a nice model material. Why? If we look at the microstructure, we have about 10% volume fraction of graphite. Here, nodule graphite. And after deformation, it's easily debonding, so we can omit it, so to say, in our simulations. We can consider it as voids from the beginning, unattended. Here you see ductile behavior. This is a particle which has been bonded from the ferritic matrix, and the ferritic matrix has some ductile dimples. And we investigate the ductile transition. Here it is for 20 degrees centigrade. You see very nicely on the fractography the bonded particles, and here the ductile dimples of the ferritic matrix. When you go to minus 40 degrees, it's important for applications of wind turbines in Arctic environments. We have already complete cleavage on the ferritic matrix, and in between we have a mixture. So here you see in situ computer tomography observation of the fracture process directly ahead of a crack tip. It is a C specimen investigated by laminography together with Dr. Morgeneier from Paris Tech. So in the middle of the CT specimen, we see how the voids and how the particles debond and how they grow. We have multiple void mechanisms, very nice. So our aim is to simulate this. Okay, we'll get back. So our friends in Germany from the BAM, they compiled all results about cast iron grades in this chart. His fracture toughness is plotted versus the graphite distance. This can be associated with our distance x0. Here in small particles and small grains, here large particles, large grains, large distances, and the fracture toughness increases with the distance, and one can fit a line here, and this is exactly our equation, yes. And if we now determine the slopes of parameter C, we come up with 2.5. Here this doesn't go to the origin because the pure ferritic matrix has also some toughness. So now was the question, the simulations up to now figure, they predicted for large porosity. Here we have porosity of 0.1 more. About 0.5 was the parameter C, and experiments showed 2.5. And this was a great challenge. We want to find the answer for it. So this is our modeling technique. So we model in a small-scale Ewing case, we apply a K field and at the corrected process zone where we model discrete three-dimensional spherical voids according to these geometrical parameters, 11% porosity, and then we come up with a certain distance of the voids. We arrange the voids in a cubic body-centered manner, and this is the softest plane, so we assume that the crack growth will go along the 1-1-0 plane. But this process zone is much smaller than our outer region, it's a factor of 10,000. I cannot draw it here. And around the course, we assume for Mises plasticity, no damage. So this is our discrete process zone, and to take into account the porosity in the outer region, we use the Gerson-Traeger-Edelman model. And to simulate, this is for simulating the ductile behavior. And now we want to go to cleavage, and then we insert here cohesive elements along the ligament and between the voids. So this is also called a boundary layer model. We have a semicircular half model, and we apply now a monotonic K field at the outer side. Here you see mesh, there's the outer mesh, and here very inside, you cannot plot it, we have our discrete process zone structure. It is a front view. Here you see the individual voids, and here's the cohesive elements, and this is the backside view. We simulate only a slide, a periodical slide, to simulate an infinite width of the crack front in mode 1 plane straight. This requires in the FEM dynamic analysis, because we have sometimes also instabilities pop in, and we apply our standard with implicit time integration. So all about the range of 1.5 million degrees of freedom, a very tiny and lot of time increments, and this requires about 1,000 CPU hours, but it can be parallelized quite well. So inserting, we do, as I mentioned, for the buttocks material, the power law hardening, and we found by appropriate steel shards exactly the ferritic matrix behavior which is in the cast iron. And now for this outer region, we take the Gerson model with also with adapted parameters. They are written here, so all the Q parameters are adapted, and I'm not going to other details. And now the cohesive element is a special development in our institute. It is an exponential curve, but we can also simulate unloading and reloading, cyclic behavior. Here, I think cohesive modeling is known to everybody. We have two important material parameters. This is the cohesive strength, so the maximum tensile strength the material can sustain. We take it for cleavage and assume that it is not dependent on temperature. And then the area under this curve is a work of separation, or the cleavage fracture energy. For our materials, DOS 400, we take two choices. So here you see simulation for perfect ductile material. So no cohesive elements, only ductile. You see nice blunting of the crack tip and how the ligaments between the voids are necking and failing. Yes. Multiple void growth. So it is only a geometrical softening, no fracture, nothing. And here you see the resulting JR curve, also normalized by x0. And here we investigate how many rows of voids do we need to describe the process zone quite well. And you see we need at least 5, then the solution converges. Compared to a simple Felices material with only one layer of voids, this gives us a toughness increase of factor of 2. It means the outer voids are reducing the hydrostatic stress state at the correct tip, and so that they increase the toughness, has a shielding effect. And this has not been considered in previous investigations. So we also can investigate the influence of the matrix hardening. Here it's clear for different hardening. The higher the hardening is, the steeper is the JR curve. It's nothing special, but we have expected it. We also can analyze different directions in the material. This is the weakest and this is the strongest direction. This leads to some branching in the easier directions. So now we compared it with experimental data. The red symbols are from various experimental data for this ductile cast iron with different yield stresses and grain or particle sizes. And these are our three simulation curves, and we see that we match the experiments out quite well, and we are with C parameter, we are between 2 and 3. So that is what we wanted to understand. And in these simulations, we did no fitting of any material parameters, only the plastic matrix behavior and the geometry of the points. Nothing else to predict the ductile air curve. So now let's go to the ductile brittle transition. So we insert the cohesive elements, and this then look at the figure. So you see cleavage in the metal, a little bit plasticity, blunting, and this is pure cleavage. And here on you see the fracture surface, how the cleavage delivers. The red colors indicate the failure of the cohesive element. So it runs through the voids. And now we can, the important relationship is now the ratio between the cohesive strength, sigma C, and the yield strength of the matrix. So we assume that the cohesive strength is constant and not dependent on temperature, and below the yield strength increases if we go to lower temperatures. That means this ratio from ductile to brittle is decreased. And here you see, so we simulate the transition regions, and the low temperature range for this relations for this ratio, we have only no blunting, pure fracture of the matrix. The crack may become even unstable. Here we have a little bit blunting, debonding of the voids, growing of the voids, and then cleavage in the matrix. And this is a pure ductile behavior, which I have showed you before. So this is R curves. They are shown here. For this ratios, the blue one is the ductile. The ratio is infinite. And if we decrease the ratio, we come to more and more brittle, and this is a very spotting of the ferritic matrix. Now we can take the initial values, so the fracture toughness, which should be measured in experiments, over this ratio. So it is low temperature and this is high temperature, and we see quite nice transition from the upper shelf down to the lower shelf. It's the the total toughness is decreased from 1 to 1/10, only by adding the cleavage. We have no weakest link model, nothing, it is all deterministic. And last slide is comparison with experiments in the ductile transition region. There are experiments in our university, but only between 20 and minus 40 degrees. These are the colored symbols. They are curves, and our simulations are the lines. We now adjusted the cleavage energy, so it's a lower shell, to this value, 5 kilojoules per meter, which corresponds to K1C of 30 megapascals per meter. This was to define the lower level, and then we had only to adjust these cohesive strengths to match all these R curves. And it doesn't look bad. So, let's come to ferritic steel. Here we look on the influence of carbides. It's clear ferritic steel has the same transition region, the same manner. We focus on these reactor pressure vessel steels. Here these are the numbers in Germany, in France, and the US. From the name it, we have nice figures here. Cleavage in the lower shell, complete ductile influence in the upper shell, and the transition between it. So we concentrate on the modern steels, which have a very low content on sulfur or manganese and other oxide inclusions, so very small one. And in that case, the carbides have a higher volume fraction than the oxides, and they are important for the fracture behavior, especially in the transition region. This is evidenced by experiments here from the French group, Tangu, on the ductile crack tip, they find here carbides which act as initiation for void formation, and these also, found same steel at room temperature. This was also at room temperature. At room temperature, it was a charted specimen. And this is at room temperature. You see the white carbides, they are broken, and from the carbides voids are formed at room temperature, and at lower temperature the carbides lead to cleavage along grain boundaries. So we take a similar model as with the cast iron. Now the difference is, because in the geometry we have much smaller particles, and the characteristic distance is also smaller, and these are now really particles, no longer voids, and we have to capture all mechanisms, cracking along the ligament by means of cohesive zones in the matrix, but then also the cracking cleavage of the particles in the blue cohesive elements, and the debonding between the carbides and the matrix. And here is the ductile behavior of the matrix, so we have all effects in. These are the parameters. So we have no initial porosity. The porosity is developing by the bonding of the carbides. Here are some technical parameters. Now the yield strength is called sigma 0. I apologize for this. And it goes for these steels from 518 to 412. We go from minus 100 to brittle and plus 60 in the upper shell. We assume again such cohesive strength assumptions. And now we can play with all these parameters. Here you see that now as our length scale between the particles even shrink to 26 nanometers. This is the final element modeling. it's more or less the same. I think I need not to go into details anymore. And these are this one result. We first assume weakly bonded particles. So yeah, we have to understand we have three cohesive strength parameters. One, strength of the particle, strength of the interface particle matrix, and strength of the matrix. Please be careful. And now we assume that the particles are weak and weakly bonded. So they have the same size, same strength as the yield strength of the matrix. And now we vary these, cohesive strength of the matrix only. And we vary the temperature. That means in effect we vary only the yield strength. This ratio, again, high temperature, high heating. My pump is too thick for this device. High temperature, high ratio, low temperature, low ratio. Let's start here in the brittle regime. You see nearly no plastic deformation, breakage of the matrix, and even breakage of the particles. And they are split. Or in the middle range, we have a little bit void growth, and a stretch zone is formed, and the oscillative bonding of the particles from the matrix. And for higher temperatures, we have complete ductile debonding of the particles in void formation. So this gives us JR curves here from the from the brittle to the fully ductile behavior for our parameter set, and only by variation of this ratio. Now we can consider strong bonded particles. Usually the carbides are strongly bonded, so we increase this ratio by factors of 3 and make the same analysis. Then we see here at low temperatures that first the matrix is fractured, and then the bonding of the particles. Then we have void growth around the bonded particles, still cleavage of the matrix. The matrix is now the weakest part, or the most ductile part. And at high temperatures, we have only debonding of the particle and no and ductile behavior of the matrix. Now we can try to compare these experiments. Here you see our results as the lines for the strong, for the weak, and for a very weak bonded particles. So again, in this consider temperature range from -100 plus 60 degrees centigrade. So we find a nice transition from ductile to brittle, and two sets of experimental data from Cotes and from Welling. I think they fit considerably well. So let me summarize. Micromechanical models for fractal processes offer us to understand the physical mechanism. I hope I can convince you that they are able to quantitatively predict fracture toughness values. However, they need a lot of information about the microstructure, the material parameters. The hope is that we can improve materials design in this way. It was not succeeded until now. The meteorological and chemical engineers have their own experience. One requires the powerful finite element software computers. For the modular cast iron, it became evident that we need many rows of voids future, what can we do? We can play now with this tool. We can apply not only K, we can apply T-stresses, or now we have an infinite large crack, but we can simulate the constraint conditions in any specimen or structural component. We can vary the parameter into microstructural parameters. We can go to strain rate effects, and we also started to simulate the cyclic behavior of cast iron, to predict the Wöhler curves. This has been today presented by Leo, and we also want to simulate the dislocation pile-up at the boundaries of carbides by means of gradient plasticity, and this was a presentation on Tuesday by Dr. Young. And I thank you for your attention.
Thank you, Professor Kuna. One short question. Yes, Professor Ricci.
You made no mention of statistics at all. You said in your cleavage grid, no weakest link. So how come you can get away without even considering statistics in these models?
It is not necessary in this model. Of course, in reality, we have statistics, which makes trouble, but it is not, the statistic lies over all the basic effects of cleavage. We have to say, withdrawn the statistics, and I think the basic ingredients are involved here. On the other hand, if you like to have statistics, you can put statistics on that. It makes the matter only more complicated.
But you must have statistics. You've got a statistical distribution of range, you've got a statistical distribution of particles, you've got a gradient in stress field, a gradient in strain field. You have to consider statistics.
So why not just model statistics, stochastic processual behavior at the beginning with some deterministic assumption? Why to make it more complicated than necessary?
Well, I would say it makes it more complicated, but not
It is more
necessary.
complicated.
I think it is a necessary approach. Anyway.
We can do it. We can insert the cohesive elements on all grains and everywhere. But I believe and put some stochastic strength distribution in our cohesive model. It is more possible. But
just you have characteristic distances in there, right?
Yeah.
Those are statistical entities. They're generated by statistics. So I don't see how you can divorce from statistics in this case. To assume the accuracy of your models is going to be profound, you have to bring in a stochastic part to it.
I don't think so, because it depends on the size relation. If the process zone encompasses many volts, many grains, then it doesn't matter. If it is very tiny, if it has only one very close to the crack, one deciding localized site, then you are right. Then all depends on the geometrical statistic and material behavior. But that's not the case, which also show all the vector toughness experiments. They find some distribution function.
Thank you, gentlemen. I will join your discussion afterwards on these topics because I'm quite interested in it. But we have to move forward to the second, and once again,